And there we go. Thanks for reminding me. So say we're interested in the effect of summer school on your test scores. The thing that you might want to do is you would just compare what are the grades of summer school students compared to the grades of other students. But we have, and so how would that look? We would have, something like your grades the following year, time, and as a function of whether you went to summer school. Okay. So, but we've got this problem, which is the error term is correlated with summer school. Can you guys think of anything that's in the error term that's going to be correlated, an X that is correlated with summer school that also directly affects your grades? Yes, it will be uploaded.
Summer classes?
Summer classes, yeah. So summer class, whether summer classes are even available. Yep. Okay. So availability. Maybe being behind. Say you're a little behind in reading or something like that. That affects the probability you go to summer school, and it also will affect your grades the next year. Maybe your motivation. Maybe your latent ability. So when we do this regression, we think that we're going to have an omitted variables problem when we're estimating beta. We think that beta is usually going to be too negative. It should be, it will be too negative. So what some people have done, some researchers have done, is they've noticed that actually you're recommended to go to summer school if you get something like below the 20th percentile in your test scores. So what they do is they plot your grades. They plot the grades of students depending on where their test scores were the year before. Okay. So all of the people on this side are not going to have no homeschool. I'm sorry, no summer school. And the folks on this side of the cutoff are going to be assigned to go to summer school. Okay, so what would happen if you plotted these is that you'd find, in general, test score grades are going to go up as their test scores from last year are going up. And you'll find that there will be a little drop right here. So in general, test scores go up as your test scores have gone up in the previous year. But there's going to be this little drop right here. And that's a discontinuity. So the line's going up, 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 and then there's a little drop. And that drop is the effect of summer school. So what they usually find is that summer school helps you be more prepared for the next year. So it's not clear why exactly. So there are two sort of theories on why summer school might help. The first is that you're just learning more. You're in a classroom. You're not. So one thing that happens that's kind of a bummer is that poor kids, their reading and their math ability tanks during the summer. So they end a school year, they're practicing every day, and their understanding is pretty high. And during the summer, they read less and they do less extracurricular stuff. So by the fall, they have actually lost some ground. There's been slippage from where they were to where they are in the fall. Wealthier kids tend to do more reading at home. And so for instance, their reading scores don't fall as much over the summer. So one idea is that just the summer school is helping you not slip as much in your skills and your academic skills. The other possibility is that you hate summer school. And so you don't want to do it again. So you keep your grades up. You kind of work harder to keep your grades up. So it's probably a little bit of both of those. It's hard to distinguish where the effect comes from, but that's kind of the idea. So I'm going to keep these notes and see if I can upload them at the end of class. But that's the basic idea is that we're going to find the regression discontinuities depend on finding cutoffs like this 20 percentile cutoff, and then plotting the outcome variable around the cutoff and measuring whether and how large the discontinuity is at the threshold where the treatment takes place. The treatment here is whether you go to summer school. Okay. So remember, we get biased estimates whenever we have endogeneity, and endogeneity takes a lot of forms. It can be omitted variables problems. It can be reverse causality, and it can be measurement error. And we have some potential solutions for endogeneity. We've used multivariate regressions where we add controls to try to address problems in our regressions. We haven't done fixed effects. Those are the two of the lectures that I skipped because you're going at too fast of a pace. But they will not be on the test. We've talked about differences in differences, where basically you have one group that undergoes some sort of treatment, and you have a similar group that wasn't exposed to the treatment at the same time. We have instrumental variables. That's what we talked about yesterday, where we try to find a variable that is correlated with the X that we're interested in, but doesn't affect the outcome that we're interested in. And then today, we'll talk about regression discontinuity, where we basically have a policy that changes because of some threshold. So in the former example, it was students that were scoring at below the 20th percentile. It's a discontinuity. It triggers you to have a treatment to go to summer school. Okay, so why is randomization good? We talked about this yesterday. Randomization, the fundamental magic of randomization is that the treatment isn't correlated with omitted variables, and because of that, we have similar people in the treatment and the control group. So what does that imply? It means that there's no omitted variables problem. And also no simultaneity. So why is that? Well, it has no omitted variables problem, because if it's random, it's not the treatment is not correlated with anything in the error term. It's totally random. There's no simultaneity, because if treatment is random, it's not affected by the Y variable. So remember, simultaneity is where we think X affects Y, but also Y is affecting X. Well, if X is random, it's not being affected by anything. So what are the limits of the usefulness of experiments? So many important policies can't be randomized. We're not allowed to randomize who's the president. We're not allowed to randomize whose parents divorce. We're not allowed to randomize who smokes, who does different drugs. In some cases, we can use regression discontinuity to provide a really nice kind of natural experiment that is almost as good as a randomized experiment. So we'll see why that is in the next slides. But here's a little preview. Imagine this example again. I don't know if you guys have ever, when you were taking the SAT or a standardized test in high school or something like that, where at the end, you're just bubbling random things. So whether you get above the 20th percentile or below the 20th percentile is a little bit random when we're comparing the folks that barely met the threshold with those that barely missed it. So these are really just like very similar people, and they accidentally got a few questions right or wrong based on how they were bubbling in at the end. And that makes it look like a lot like a randomized experiment where the people are being randomized into summer school basically based on whether they got a few extra questions right or wrong when bubbling in randomly at the end. So this is another kind of famous example. Suppose that babies in the hospital are provided special care if they're low birth weight. So this is something that we do, is that if a baby is born at less than 1,500 grams, they're considered to be a little tiny baby, usually premature. Either premature or the mother is very heavy, very morbidly obese, which is ironic. So you'd think that heavy moms would have heavy babies, but the extra adipose tissue around the stomach makes it so that the baby receives less nutrients, less blood flow. So what happens is that there's a special care involved when babies are born with low birth weights, and the baby's kept in the hospital for a longer period. They're usually given oxygen and more kind of nutritious supplements and things, and more frequent appointments over the following year. And say what we were interested in is estimating the effect of this special care on a baby's health 1 year later when the baby is 12 months old. Oops, sorry, I didn't mean to, I shouldn't have deleted that. But so what can we do? Well, first, what we might do is the simple thing before we think about the regression discontinuity is just to regress the health score of the baby on whether they get the special care from being low birth weight. So here we would actually probably expect, what do you think? Do you think that they getting special care will be correlated with having a higher health score at year 1 or a lower health score at year 1?
I guess if you got more health care, you would have a higher score.
Okay, so we think that beta 1 might have a positive effect. Here, that's exactly right. I think that we think that this special care should be having a positive effect on the health score. What's going on in the background is an omitted variables problem, which is that low birth weight babies are going to have received special care, and also being a low birth weight baby predicts lower health scores. So we think that special care is, it might be biased. So we think that beta 1 will be underestimated. So actually, it could be the case that those that receive special care are going to have worse health scores than people that didn't receive special care on average, because those that didn't receive special care are really healthy babies. They were healthy babies to begin with. So what sign do we think that beta 1 would have if we actually estimated the regression for all newborns? I would guess that actually the beta 1 that we estimate, so I'm going to say this star, because not the true beta 1, might actually be negative, because very small babies are less healthy actually for the rest of their lives. They can look at moms who had big babies and little babies. So it's the exact same genetics, it's the exact same family, but the babies that were born littler are less healthy and live for shorter periods for the and go to less school. Lots of interesting things. They have worse health, more likely to have asthma for the rest, more likely to actually, this is interesting too, Low birth weight babies are actually more likely to be obese. It's another kind of interesting, weird thing. So why is this? Why could we get a beta 1 that's actually negative when we think that the effect of special care is positive? It's because of the omitted variables bias problem. So we think that there's the birth weight or baby health is correlated with special care and directly affecting the kid's health later on. Does that make sense? I just want to make sure that's kind of clear. Ibrahim, Katrina, Kimberly, Leanna, Levi, Manuel, Noah. Okay. So what sign will beta have? So in this example, if we just did a simple regression, we would actually probably find, like if we drew a line through these points, I'm thinking we would get something pretty flat actually. So we would find in the regression, we would get a 0 beta or something close to a 0 beta. But actually, we should think about this not in terms of comparing all the babies, but comparing babies that were close to the threshold here. So these are pretty small babies that didn't get special care. And these are small babies that aren't very much smaller than these babies on the right-hand side of the threshold that did receive special care. And there's actually a pretty big difference between the averages of these two groups and their health score a year later. And so that's kind of the intuition of the regression discontinuity, is instead we can fit a regression line like this and then use the predicted value here and the predicted value here to calculate what is the difference made by getting this special care. This is related to a hypothesis called, what is it called? I call it the early life hypothesis. So it's this amazing branch of research that shows little tiny things that happen when you're in utero. That means when you're in your mother's womb, or when you're a very small baby, or even a small child, have enormous effects on the rest of your life. So whether your mother experienced mourning while she was pregnant with you, like if her mother died while she was pregnant with you, you would have worse effects than worse outcomes than if your mother her mother died just after you were born or just before she became pregnant with you. So and it has to do with kind of the stress that mom's body undergoes when she's mourning. That's not great for the kids. Lots of other things, little changes in nutrition, little changes in special care when you're a newborn baby. Breastfeeding is kind of famously very good for babies, and just kind of a different, they tend to have less allergies, for instance, and they healthier weight gain. Not all moms are able to breastfeed, but those that can often do. Suppose that we estimated a regression line on each side of the cutoff, and we use this line to predict the score at the threshold. So that's what this is. We use these lines to predict what's the health score as we are getting, as weight goes up towards 1500 from the left. And then what is the predicted health score as we're approaching the threshold from the right. And then we use these two predictions to compare and calculate what is the effect of special care. Okay. So the RD, the regression discontinuity estimate, is the gap between the predicted value at the cutoff as determined separately on the left and the right-hand side. So we're going to estimate a regression line on the left, a regression line on the right, predict what the value is at the threshold on the right and the left, and then use the difference to calculate the effect of the treatment. So that is the regression discontinuity. That's what we're doing. So it's very simple, very clean. The regression discontinuity paper is basically the main figure looks just like this, where they're plotting the outcome across the threshold and seeing how it changes. Okay, so what is a regression discontinuity? We call it a kind of quasi-experimental design. It means quasi-experimental means it's like an experiment. It performs like an experiment. It measures the causal effect by assigning a cutoff above or below a cutoff that assigns some sort of treatment or some sort of intervention. So why is this kind of convincing? Well, subjects just above and below the cutoff are very similar. So if we think about the person that gets 1400 on their SAT, this is a very similar person to those that are scoring a 1390 on their SAT. So if we use if there's a scholarship that is triggered when you get a 1400 on your SAT, we can use the folks that got a 1390 as a very good control group because they're so similar in so many ways. Subjects on the treated side of the cutoff are exposed to the intervention, and those on the other side aren't. And so the difference between those two groups at the cutoff can be attributed to the intervention and not to other things because they're so similar. So the whole logic of the randomized control trial, or the RDD, is that the treatment and the control group are so similar in every other way. Any differences in their outcomes must be from the treatment. It's not from some omitted variable. Okay, so what are the assumptions that we make to have a good RDD? And we try to test these as well best we can. So the two things that we need is that we need a cutoff and the assignment variable. So in our first example, your test score in the previous year is the assignment variable, and then the cutoff was 20th percentile. The assignment variable in our recent example is the weight of the baby at their birth, 1,500 grams. And the cutoff needs to be sharp. So what that means is if we had two kinds of cutoffs, you could imagine a kind of soft cutoff. So what we need, the ideal is we have no one being treated on one side and everyone being treated on the other side of this cutoff. So you could imagine that this threshold isn't really a rule, it's like a guideline. And so some doctors are doing treatments for babies that don't meet the criterion. So this is just an example. This is actually, I put it the wrong way for the birth weight example. But this one is we would call sharp. And this one is not sharp. What does not sharp mean? It means that there's not a discontinuity in the treatment at the threshold. So this just looks like a kind of a straight line. This isn't a straight line, this is a jump, a discontinuity. So that's really important. The other thing we have to assume is that people can't manipulate which side of the cutoff they're on. So imagine that instead of it being your birth weight, say it's when you came into the office, when you came into the to the hospital to have your baby born or something like that, whether you came before noon or after noon, but people knew that. And so if they wanted the special treatment, they could come before noon if that was the cutoff. And if people didn't want the treatment, they could go afternoon. So that would mean that there is a discontinuity. If you come before noon, you get the treatment. If you come afternoon, you don't get the treatment. But it's manipulable. So we're back to the world where we are in a problem of selection, where basically people are choosing whether they get the policy, the intervention, the treatment or not. And so that reintroduces an omitted variables problem. So what we have to have is some kind of variable that's hard for people to finally control. So the birth weight of your baby, if the birth weight of your baby were 1501 grams, and you wanted the special treatment, first of all, you couldn't know that before the baby was born, and second, you couldn't manipulate it so that your baby lost 2 grams to qualify for the treatment. So that's a nice example. The test scores is also a good example, because if you are, you don't know when you're taking an exam, it's not like you know what your test score is as you're completing the answers. So why is assumption 1 so important? Assumption 1 is important because that produces a treatment group and a control group for comparison. So if we have this, we don't really have a treated group and a control group. The people on the left have been treated, the people on the right have been treated, and they're treated pretty similarly. So we don't have this nice thing where we're looking at similar people that have different treatment exposures. Why is 2 important? 2 is important because if subjects can choose their treatment status, then we have selection, or omitted variables bias again. Okay. Any questions there? Just see here. Okay. Okay. So how is the RD similar to and different from a randomized control trial? Well, the similarities are that subjects don't choose whether or not to be treated. And we think that close to the cutoff, the subjects are as good as randomly assigned. So whether you were born with a birth weight of 1,500 or birth weight of 1,499, we think that that is basically randomly assigned. And we can check for a first stage effect, the treatment group is actually getting treated. So what are the differences? The treated and the untreated groups are not balanced on average. So we know that those on the left and the right might differ by a little bit. So one thing that's in a randomized control trial, you'll have, people with every score, for instance, getting summer school. In our regression discontinuity, you will only see people with low scores getting summer school. So it's actually one of the bummers about regression discontinuity is you can only measure the effect for people who are basically at the threshold. So that's one of the drawbacks. And so that's the second thing, is that you can only get an estimate of the treatment for subjects very near to the cutoff. So we're not able to estimate, for instance, the effect of summer school on people who had high test scores in the year previous. So it could be that summer school is much more effective for those people. It could be that summer school is much less effective for those people. And it could be that they have the exact same effect on high score high scoring students as low scoring students. So what does the regression look like? What we have is two variables. We're going to introduce a third variable. So the first variable here is, we call this distance to the cutoff. Where x is the variable used to assign treatment. Okay, so say in our first example was the percentile of your test score in some grade, third grade, and then C is the cutoff. So that would have been the 20th percentile. So say I scored in the 30th percentile, my distance variable would be 30 minus 20 equals 10. Okay, so say I scored at the 10th percentile, 10 minus 20 equals negative 10. And say I scored at the 20th percentile, then my distance to the cutoff would be 0. Okay, so all we're essentially doing is making it so that 0 is where the cutoff happens, and then we have positive values if you're above the cutoff and negative values if you're below the cutoff, and we're just going to control for how far people are from the cutoff. So that's going to give you kind of a straight line like this. Okay, and then the treatment is just whether you're above the cutoff or not. And so that treatment variable, the coefficient on it is going to give you beta 2, and the slope of this variable of this line will give you beta 1. Okay, so that's the basic regression discontinuity format. Or just to make sure that we've nailed everything down. Y is the outcome variable, so it could be grades in our first example, could be their health, a kid's health score in our second example. X minus C is the distance from the cutoff, which can be positive or negative. T is a binary variable, which is 0 if the person's treated and 1 if the person is not treated. And it doesn't really matter how we write it. We can name the variables anything we want. So instead of xi minus c, we could just call it distance, and instead of t, we could just call it treatment. So that just makes it a little bit, just how you write it doesn't really matter how you write it in your regression. So there are other things that we can do. So maybe distance doesn't have a linear relationship with the outcome variable. Sometimes people put in lots of other controls of just, so not just distance, but distance squared, distance cubed, and which would allow for the relationship between distance and the outcome variable to be curved. So say we had something like this. So this would have a discontinuity there, but because the relationship between distance and the outcome variable y isn't linear, we need to introduce these flexible quadratic and cubic terms to allow our line to match the curvature of the data. So that's one thing that people do. Another thing that people do that's actually, this is probably the most common thing that people do, is that they have two different lines that they estimate. So this is the main problem that sometimes happens, very common. Big problem is we've got some sort of cutoff, and the data are going up here and they're going down here. Okay, so if we only allowed for there to be one slope, we wouldn't be able to actually match this data. So what we do instead is we allow for one line to be on the left and a different sloped line to be on the right. And then we're still going to use these to predict the values at the cutoff and measure that distance as the effect of the policy. So how do you do that in a regression? You include the distance term like we have before. And then you include a second term that is the interaction between treatment and distance. So what does that do? All that does is it allows for there to be one slope on the left side and a different slope on the right side. And you're still going to have the beta on treatment will still be the effect of whatever the intervention is in the discontinuity. Okay, so let me stop for questions. Noah, Levi, Leanna, Kimberly, Katrina, Ibrahim, Esmeralda.
I think the only question I have is why is there a TI on the beta 3 and not an X minus C?
I'm sorry, say it again. Why is there a TI?
Yeah, on the
Okay.
beta 3 rather than a treatment X distance.
Oh, yes. So I should have an I here as well. So I just means that treatment will vary by for every person in the data, they will have their own treatment value. It'll be either 0 or 1. All it means that when you have an I is that it can be different by person.
Okay.
So does that make sense? So the XI means
I see it now.
every person has their own X value. Every person has their own treatment value. They're not, yeah. Yep. Okay, so let me just say this. What does the beta 2 reflect? It reflects the change in the slope on the treatment side. So here we'd have one slope here and a different slope here, and the beta 2 will reflect the change in the slope from the left to the right. Other questions here? Let me check. Can you explain the exponents on the variables? Yeah, of course. So I think you're talking up here. Is that right? Secret writer. Okay, awesome. So remember from before the midterm, we talked about allowing for curvature in the data. And the example was that we would regress wages on experience and experience squared. And so to do that, all we do is we generate a new variable in the data that is experience squared. So if someone in the data had 1 unit of experience, their variable called their value in experience squared would be 1 times 1, which is 1. If someone in the data had an experience value of 2, their value in the experience squared column would be 2 times 2, which is 4. So it's just, we generate these by multiplying here distance by itself or distance by itself 3 times to generate those different variables. Okay, so here's back to our example on newborns. We've got newborns are assigned to special weight care if their weight is equal to less than 1,500 grams. And here's our regression coefficients. We have that the distance has a positive coefficient, and this is going to be statistically significant. What does this mean? This just means that, oh, that's weird. This just means that that as babies get heavier, in general, they have a higher health score a year later. And that's true. We find that to be, that's a very robust kind of empirical finding, very common. We've also find that the coefficient on treatment is 1.64, and that will also be statistically significant. What does that mean? That means that the jump at the threshold is 1.64. So the health score is going up by 1.6 at the threshold. Does this satisfy our two assumptions? Is there a cutoff in the assignment variable? Yes. Subjects cannot manipulate which side of the cutoff they're on? I would say yes. I don't think that moms can determine, or babies even less, can determine what side of the weight threshold that they're on. What is the regression discontinuity estimate of the effect of special care? It's that the health index increases by 1.64. Is this effect statistically significant from 0 at the 95% confidence level? Here, all we're going to do is say 1.64 minus 0 and divide by the standard error of the beta. And we're going to get something that's greater than 3. Is that statistically significant? Yes, significant. Because 3 is greater than 2, which is usually our cutoff. Okay. So it becomes legal, as many of you know, to purchase and consume alcohol when someone turns 21 in the United States. And researchers are interested in understanding the effect of turning one on various outcomes like traffic accidents, arrests, and job performance. So what we might do is look at people who are around their 21st birthday and see if there are differences in their in driving drunk or showing up late to work, et cetera, et cetera. So what's our running variable here? It's their age. So how do we know? It's this one. It's the variable. What's the running variable? The variable that determines whether you're treated. So here, what does that mean? You're treated, you become alcohol eligible if you're over 21. So that's the treatment, is being over 21. So the age is the running variable or the assignment variable. Does this satisfy the two properties we need? Is there a cutoff in the assignment variable? Yes. Can subjects manipulate what side of the cutoff they're on? Nope. You can't make yourself a day older or a day younger. So there's very hard to it would be hard to manipulate. So suppose we had arrest data that looked like this. What can we conclude about the effect of turning 21? So here we've got a threshold at age 21, and we've got young, usually young men who are just younger than 21. And we've got young men that are just older than 20. Sometimes young women, but most of the time it's young men. And so we've got these barely 21-year-olds who have a much higher arrest rate. So what would our regression do? Our regression would be fitting a line to either side of this cutoff like this. And then we would be thinking, okay, well, the effect of alcohol on arrest rates is the difference between the prediction of the arrest rate from the right-hand side series to the prediction of the arrest rate from the left-hand side series. So that's the effect of alcohol legalization. Okay. So it's not exactly the effect of alcohol, because not everyone on this side is drinking and not everybody on this side isn't drinking, but it's the effect of the legalization. It's the effect brought on by making it allowable. Okay. Questions here? So we fit the regression on either side of the data, and then we'll look at something like this, and we will get an estimate that looks like this. So what's the effect of turning 1 on your probability of getting arrested? it increases the odds that you're arrested by 0.015, which is 1.5 percentage points, or more, I'm sorry, or what is that as a percent? It's a huge, you think this is a small coefficient, but this is a huge coefficient. Your latent odds of being arrested are 2%, and the effect of crossing this 21 threshold is almost as large. So that means that you're almost doubling the probability that you're arrested. What's the probability of getting arrested if you are 20 years old? Well, we can just plug in 20 to the age, and for treatment, of course, 20-year-olds are not treated. So we'll get 0.021 plus 0.002 times -1 is equal to 0.019. What is the probability of getting arrested if you're 22 years old? So we can plug in 22 here and do the same math. 0.021 plus 0.002 times 1 plus 0.015. Why is this here? Because 22-year-olds are treated. And here we'd find 0.023, 0.038. How much of the predicted difference is due to the trend in age? So the difference, how much of it is due to the trend in age? Well, the easiest thing would actually be to calculate the difference that's due to the treatment effect, and then the residual would be due to the trend in age. But you could also just multiply 2.002 times 2. And that would give you 0.004 is due to the trend in age. Does that make sense? Is that handy? Warren, Stephanie, Saul, Noah. Okay. Okay. So we'll just talk about this and then we'll take our break. So the main consideration for regression discontinuity is actually that we're estimating what's called a local average treatment effect. And all that means is that it's the effect for a very specific subset. So for instance, the effect of the special care on low weight babies might not be that which we find if we gave the same treatment to high weight babies. So it might be something where like a healthy baby isn't affected, just like a person without a headache isn't affected by Tylenol. A healthy baby might not be affected by treatments meant to help low weight babies. So what we're always thinking about when we are doing regression discontinuities is, who is this estimate about? Who is this estimate about? So we're essentially estimating the effect among a special group of people that are near the cutoff. The effect far above or below the cutoff could be super different. And so giving normal weight babies special care could have no effect. Allowing 6-year-olds to drink might not have an effect on their arrest rate. So we're looking at, we're finding an effect that's kind of specific to a certain group of people. So if the policy were expanded or changed, we can't assume that the effect will remain the same at different cutoffs. Okay. Let me just remember what the second consideration is. Okay, so this I'm not going to do these two. Okay, so let me stop there. I am going to go get a little snack, and then we will be right back. I have these two lizards doing a mating dance. It looks like they're one of them bouncing up and down, and the other one is doing up dog, and it's kind of entertaining. It's fun. Okay, let me, and I will just have a little podcast that I thought was interesting. I'll play while I'm getting a snack.
Theodore Dalrymple first. It's easy to show that equality is not an end in itself, but can be desirable only in conjunction with some other goal that is desired. If an entire city were destroyed, for example, everyone would be equally homeless. But this is not a desirable state of affairs. If we were able to reduce the infant mortality rate of the richest and the poorest decile of the population by 1 per 1,000 live births, this would actually increase inequality. But no one, I think, would refuse to do it on those grounds, as increased inequality. A state of equality of outcome would be grossly unjust and psychologically disastrous. It would deprive life of a large part of meaning. To disconnect entirely reward from desert would mean the destruction of the concept or part of the concept of justice. And even if you believed in the most rigid determinism that A managed to do better than B only because of his genetic endowment and his circumstances, still not to reward him would deprive him of a reason for trying to do his best, which would cause everyone to lose. And the case is even worse with equality of opportunity. The only real way of ensuring equality of opportunity would be to have only clones as children and to bring them up in hatcheries. I don't think it takes much effort of the imagination to realize what such a society would be like. I've been to North Korea, and I can assure you North Korea would appear like a haven of liberty by comparison with that. On the other hand, the goal of giving everyone opportunity, though not equal opportunity, should be aimed at, in my view. I hope I'm not alone in finding it scandalous that so many of our children leave school unable to read or write fluently after something like £80,000 has been spent on their education. Practically all children can be taught to read properly, and our failure to do this is far worse than any present degree of inequality. Equality of opportunity in a truly meritocratic society would have harmful psychological effects, moreover. In such a society, if it allowed inequality of outcome as well as having equality of opportunity, we could blame only ourselves for our failure. The need to be able to blame someone else is a fundamental human need, if not a right. Clearly, there's unjust inequality. If I were to arrange for all your cars to be stolen, for example, made over to me, that would be my unjust enrichment. The exact degree of equality, other than formal equality under the law, is never specified because it is unspecifiable. Clearly, there is unfair inequality as well. It's unfair that I was not born more handsome or more gifted than many other people I could name. And furthermore, we must remember that justice is not the only desideratum in life.
The reason that his meritocracy, in his view, of course, it's a satirical book. This is not a compliment, meritocracy. It says that the reason that society is dysfunctional and disastrous is precisely for the reason you give, which is that if you've failed on your own account, then that's a truly terrible thing. And there's a sort of snobbery at the people at the top who have not only made it to the top, but they deserve to be at the top. And they look down on the dysfunctional.
Psychological problems. My point is that I think that we are distracted by the notion of equality from doing those things which are very much easier. So we can, for example, increase people's opportunities. I don't think there's any doubt about that. So I find it, I worked in an area where almost no one could read what I would call fluently. And that seems to me something that should be easy to change. And it seems to me that people who are given that kind of education have almost no opportunity. It's not a question equality of opportunity, they don't have much opportunity in the first place. And it seems to me that that's a true scandal, because it's been proved that you can change that. You can teach the vast majority of children.
But the advocates of equality of opportunity would simply agree with you, wouldn't they? They'd say, well, yes, you're quite right. We're never going to have equal opportunities until people can read.
Yeah. But I think the difference is I'm not seeking equality of opportunity. I'm just seeking for those children to be educated so that they have at least some opportunity. They're never going to have the same opportunity as people born elsewhere, but at least they will have some choice. They won't even be able to answer the telephone properly.
Can I give you one?
Okay. Welcome back. Any questions? Any questions from all that? Any questions on regression discontinuity, I mean? I'm just gonna, okay, cool. So let's do a little review, next half an hour or so. So some of this should look just kind of old and happy. So this is all from the second half of the class, so nothing from the first half. The first half, you're welcome to go back and look at the recording of our review for the midterm. And also, I do think that at this point, most of that material is kind of cemented in your mind, hopefully. So, so usually, you know, we are trying to figure out whether our sample means and whether our estimates are statistically significant. That means whether they're statistically different than something that we thought that they might have been. So in sample means, we could have, we usually have a hypothesis, which is, we think that we think that the average UC Merced student is studying 30 hours a week, and we can go out and collect data and see if the data are consistent with that or if they reject that hypothesis. In regressions, we are often asking whether the beta that we're interested in has an effect that is different statistically than zero, whether the data is inconsistent with a zero relationship. So, so what's interesting is that both sample means and regression coefficients will have normal distributions. So the sample means, that means if we keep going out into the world and taking a new sample and a new sample and a new sample, those sample means will be normally distributed. That means that if we plotted them out, they would look like a bell. And the middle of that bell would be over the true value, the true population value of the average according to the central limit theorem. So the central limit theorem is important. This will definitely be, oh, shoot, okay, sorry. Screen, share. Okay, can you see now? Okay, so the central limit theorem, all it says that it is as we get more and more samples from more and more random samples, and we calculate the sample mean for all those sample means are normally distributed, and the true population mean will, and they will be distributed around the true population mean. Okay, so that's the central limit theorem. There is a question on the central limit theorem in the test. So it's just, all you have to know is that if you keep taking samples, The means of those samples are normally distributed around the true population mean. That's all it means. The regression coefficients that we estimate are also normally distributed. That means if we keep going out, taking a new sample and then estimating a regression line, take a new sample, estimate a regression line, the betas that we get from those regressions will be normally distributed and they will be centered around the population mean. So that's just kind of the flip side of the regression version of our estimates. So when we're calculating our t-statistics, we will have the sample mean that we calculate. We'll have basically our hypothesis about what the sample mean, what the population mean actually is, and then we will divide the difference of those two by a value that is the standard error of the sample means. That will be distributed as a t distribution with n-1 degrees of freedom. So if I had you go look at a table, which I will not have you do, you would be looking for the sample size n-1 on the left, and then looking for the critical value at the confidence. So say so this is usually n's over here and the confidence level over here, and yeah, that's you would be looking. So say I had 40 people, so I'd be looking in this row, and say I was looking at the 95% confidence level here. I'd be looking, and in that little intersection of those two lanes would be the critical value that I would use to calculate, to determine whether t-statistics were statistically significant. Okay. So the regression coefficients are normally distributed around the true population parameter, and the t-statistic for regression is actually exactly the same idea as we had for sample mean. So we're going to take our estimated beta, we're going to subtract off our hypothesis for what beta is, which is usually 0, and then we'll divide by the standard error of beta. The only difference is that the degrees of freedom isn't n-1, but n-k-1, where k is the number of slope parameters in the regression model. So that's just how many degrees of freedom there are in our regression. Any questions on that? We haven't looked at where the standard errors for beta come from in our regressions, or at least we haven't. So we stated in lesson 10 that if the regression errors are normally distributed, then the coefficient estimates are also normally distributed, and then we can do hypothesis testing. So okay, so the variance of u, we usually call that sigma squared, and we can show how to calculate the standard errors of the betas depending on the sigma and how to compute both of them. So I'm not going to I don't think I'm going to ask you to do this on the test, but just so you know where our betas come from. So first, our estimate of sigma squared is just, we're going to square all of the predicted errors in the regression, and then we divide it by n-2, and that's how we find sigma squared, our predicted variance of u, and then the variance therefore of the beta of our estimate will be that sigma that we estimate divided by the variance in x. This is the variance in x. X variance basically in residuals. And that gives us that gives us the variance of our beta. So we already saw how to estimate sigma squared. And then we're not going to do that the next few parts, but that's just basics. I don't think I'm going to ask you to calculate the variance of beta. If I have that on the test, I'm going to go through the test again right after class. I'll take anything out that asks for you to calculate the variance of beta. Why should we be concerned about outliers? So this is definitely on the test. Why are we concerned about outliers? Why in an ordinary least squares regression are outliers a big deal? The reason that they're a big deal is that OLS, ordinary least squares regressions, are minimizing the sum of squared errors. So an outlier has an enormous effect on the slope that you estimate, and even on the intercept that you estimate, because outliers have an outsized effect on the regression slope. So why is that? It's because say we had these 10 points or something like that. And we have one point right here, okay? If we just calculated the sum of squared errors, if we drew the line through the rest of the points and we calculate what's the sum of squared errors here, it's going to be maybe thousands of times larger than any of the sum of squared errors over here. So it's going to have a huge pull on this regression. And it's going to make us draw something a lot more like this. Okay, and that's all because the influence of a point has a what's it called? A quadratic effect in how far it is from the line itself. So these points that are very close will have very small effects on where they are because they're close. Any point that's far from the regression line is going to have a huge gravitational pull on where that slope parameter goes. So the key is, if I asked you, why do outliers have a big effect in regressions? It's because a regression, why? Because the regression minimizes squared errors. So outliers are enormously influential. Why are they enormously influential? Because their squared errors are big, they're huge, they're enormous. And we did an example in class where I just showed you if you had a squared error that was far, it's going to have a very big, this example down here. If you compare these two, you'll see how much bigger the regression line, how much more sum squared residuals are there from a big outlier than a small outlier. Okay. So we did this example in class. We've got if you just kind of ignored the outlier, you'd probably do a regression line like this. If you include the outlier, you'd probably get something more like this. And so this one outlier is having a huge effect on the slope parameter. And we saw also that it had a big effect on the R squared. I was going to show you one thing. I can't remember what it was now. Okay, let me just show you one little thing. So imagine instead, just so you know, see the effect of an outlier compared to a normal point. So say we had this, we're ignoring this outlier. And say now we also ignored this point right here. What would the regression line look like? It would look not very different. It might look like that. So the difference between an outlier and every other point in the data set is that an outlier is going to have a huge effect on the regression. Okay, so this is with with the outlier, the red line. That's what makes it an outlier. It's not whether it's miscoded. You could have miscoded data. They're actually not outliers. It's any observation that is whose inclusion significantly changes the results of the regression. Questions here? We wish to estimate the effect of company sale. Okay, so this is the same thing. So I basically have gone through all of the outlier bit already. I'll just show you really quick. So when we include the regression, the outlier, we will have a, I can't remember which is I think it's this one. This is insignificant. The R squared is pretty small. When we drop the outlier, the R squared goes up by more than double. And the coefficient here goes up by also more than double. So, and now this is also statistically significant. So those are three ways in which an outlier can change the outcome of a regression. It changes the slope, it changes whether the slope is significant, and it can change what the R squared is by a big amount. So why these changes occurred? They occurred because the outlier, this is the way statisticians call it, was super influential. It had a big influence on the slope parameter. Okay. So this is another, we talked about this, I think this was just after our outlier slide. There were some practical considerations when we do regressions. So one of those is just when we are doing prediction, we feel less confident about the prediction if we're predicting out of sample. So the example was like, say I had people that were, let me think, that's a good example. Say I had the height of people in high school. Okay, so I have and the people in high school are mostly between 5'5" and 6 foot. And I used those and I made a line that predicted their income based on their height. Okay. And then you come to me and say, I have Shaquille O'Neal. And Shaquille O'Neal is how tall is he? 6'5" or something like that, 6'5". How much will he earn based on his height? So the question is whether the variables here, the people that I have here, their heights are predictive of someone who's might be much taller. So we mostly feel confident about making predictions within the kind of domain of the regression that we run. So we might be more comfortable predicting income for people between 5'10", 5'5", and 6 foot than we would be people that are 6'5" or 7 foot. And Shaquille O'Neal is kind of a bad example because he's got all this other stuff that's not related to his height that's affecting his income. Okay. So there are two reasons why extrapolating out of sample can be messy. The first is that we might have the wrong functional form. So that's a very fancy way of saying the following. So it could be that height has a kind of a positive relationship in the normal range, but not in the higher ranges. So it could be that you see something like this, that very tall people have lots of back problems, or they have actually very tall people are more likely to have cancer. They don't know exactly why that is. It might just be that tall people have more cells that can go wrong, and that's where cancer comes from. They have more back problems. The very tall are more likely they die earlier, actually. So it could be, we're estimating here, and actually there's that's not the right functional form. To have a straight line go through those kind of just the lower end misses the fact that if we actually had taller people in the data set, that we actually might get a bend. And the bend can work anyway. We could have bends that go like this too. We could have any sort of shape on this. So functional form is the first problem. The second problem is that we could have omitted variables. So it could be that people with very different values of X could be super different another way. So for instance, if we were predicting, I don't know, the amount of spending that people do on their children based on their test scores in high school or something like that. So we have these, we have these predictions, and then I show you, actually, Shaquille O'Neal is a good example here, that Shaquille O'Neal has a lot of unobserved stuff that makes him higher earning as a professional that you wouldn't have predicted from high school. Bill Gates, so maybe he has a test score that's not very different than other people, but his income is so high. Dr. Shaq, exactly. His income is so high, or his influence is so high, or his work ethic is so high that other things about him won't be very comparable to the group in our sample. Okay, omitted variables bias will be on the test in numerous ways. So this is definitely, if this feels foggy or shaky or anything, this is a really important area to review. So say our quote unquote true model is that we have an X1 and an X2, the two variables that both affect Y. But because of some imperfection in our data, we're not able to include X2 in the regression. Okay, so what we're able to estimate is these beta stars, beta 1 star. And we write the relationship between X2 and X1 in the following way. So there was a question on the midterm that guffed a lot of people, where I asked, what is the coefficient delta 1? And the coefficient delta 1 is the coefficient on X1 in a regression of X2 on X1. That's important. And this just expresses X2 so that we know what X2 is in terms of X1. And what that means is that when we can rewrite the regression to figure out what the bias of our estimated beta 1 will look like. So here we have the true model includes beta 2, X2. We can use that X2 formula that we had before, where X2 is equal to delta 1, 0 plus delta 1, X1 plus eta. And so we're going to put this in from X2. And then all we do is we'll multiply through beta 2 and collect the terms. So what are we going to collect? We're going to collect all of the terms that are constants. So terms that don't have a variable in them. So beta naught and beta 2 times delta naught will be a constant. And we're going to collect all the terms with an X1 in them. And we're going to collect all the terms that have an error term in them. Okay. So all of the constant terms together will form our estimated beta naught. So our estimated beta naught will be the true beta naught plus an error. This is our bias term. Will be off a little bit. It will include our delta naught. Our beta 1 is usually the thing that we're most interested in, and it will include the true beta naught, but it will have a bias term, which will be the relationship between X2 and Y, and the relationship between X2 and X1. And then we don't really do much with this, but the error term will also be a little bit different. than we had before. So this is the formula that you really want to know. And it's that your estimated beta will be the true beta plus this bias term. So if the beta 2 is positive and the delta 1 is negative, then our beta star will be less than the true beta. What does that mean? It means that our bias term will be negative. We'll be underestimating the true beta. If our beta 2 is also negative, then the bias term will be positive, and instead we'll have our beta star, our estimated beta, will be overestimated. Okay. Okay, so almost every regression that we've saw in the first half of the class had an omitted variables problem. When we were regressing wages on years of education, we were omitting ability. When we were regressing house prices on pollution, we were omitting urban or rural. When we were regressing CEO salaries on profits, we were omitting things like company size. That was kind of always in the background, but we didn't worry about it at the time. Reverse causality is similar to omitted variables bias, but it's a little different. We sometimes call it reverse causality or simultaneity. And it's when the explanatory variable is a function of the outcome, and in addition to being the outcome variable, a function of the explanatory variable. So the classic example is that we think cops affect the amount of crime that happens, and we have good evidence that that's true. More cops reduces crime, but we also think that cities that have more crime are likely to hire more cops. So we might find this sort of strange thing where it's actually in very violent cities that we see the highest police per capita share. So suppose the problem is that police might be affecting crime, but crime is also affecting the number of police in a cross section. So that makes it very difficult to figure out what's the causal effect of police on crime. So we've been talking about instruments. One of the interesting things that they found we talked about instruments for kind of figuring out simultaneity. They found that mayors hire more police in election years because it looks bad. If you're following the Gavin Newsom recall election, the support for recalling him is surging, and part of it appears to be just the explosion of crime. There's been hundreds of additional homicides, burglary, theft, rape, every form of crime has exploded in the last year, and this appears to be part of the reason that he's polling very badly right now. So what do mayors do is they tend to hire more cops in election years. So if we were doing an instrumental variable, what we could use is an indicator for election year. And remember, instrumental variables need two things. One, they need to be related to the X we're worried about. And two, they need to be not correlated with the error term. So that's here, they can't be correlated with anything that affects crime. So our election years, do election years have an effect on crime? I don't know, I'm not sure about that. But we do know that election years are related to how many police there are in a town. So when they use election year as an instrument on police, they find a negative beta, basically that there's less crime in election years because there are more police. So it's kind of an interesting thing. Okay. So I am going to stop here and take questions in the last 5 minutes or so, in case you guys have anything you want to talk about.
Will you have a review session tomorrow at 9 again?
Yes, we'll have a review session tomorrow at 9, but it's mostly going to be it's going to be a question and answer session. So if you don't have questions, it will be a very boring review.
Okay, all right. Thank you.
Yep.